Good morning. My name is Michael Bai. I'm one of the founders. I'm the Vice President of Engineering. Today I'm going to talk about the 128T data model, and I think it's important to really cover the basics of how we structured the concepts around configuring the 128T platform. And I think that's critically important to really understanding how secure vector routing works. I'll go through a number of these concepts, but the 128T data model really is the language of SVR. It defines the services, the tenants, and the associated policies. Adhering to the principles of named data networking, we've taken a different approach that really tries to use natural language to describe intent rather than leveraging entirely IP prefixes or CIDR blocks to describe the network from a bottom-up approach. We've taken a top-down approach to defining networking. A lot of the concepts here are going to seem foreign and abstract. You know, they come from sort of a computer science background. And we've spent a lot of time defining the terms to apply meaning to the new concepts of routing that we've come up with. And they're different not for different sake, but really we felt that they were necessary to really provide context to our new approach to secure vector routing. I'm going to do my best to go through each of these concepts. Feel free to ask any questions along the way. And I hope they make perfect sense as I'm wrapping up. To start, our data model could be broken up into sort of two logical groupings. We have some concepts, the outer box, the authority. Everything is wrapped up into an authority. And authority is really, could be thought of as an administrative domain. It's the entirety of your network. It comprises a conductor platform, which is our orchestration monitoring piece of software, as well as the entirety of all of the routers, the 128T routers. Within a router, I'll go into more detail here, but we have this concept of nodes. You can have either one or two nodes to achieve maximal redundancy and throughput throughout your network. And then we have a group of constructs that are local in nature. And what I mean by local is that they apply only to the 128T router instance, while the conductor has the entirety of the view of the configuration for your entire administrative domain. I'll go into each one of those concepts. At the heart of the 128T data model, as we've mentioned, is this service-centric approach. And we take a different approach in that the 128T data model is a deny by default instead of traditional routing, which is really connected interfaces allow you to communicate to your devices implicitly, and then you have to set up access policies to deny the entities that you don't want traffic on your network. One of the upsides to this is a lot of our customers actually don't really know what traffic's in their network. And after going through the exercise of deploying a 128T router, they really come to realize, wow, I didn't realize I had all this other traffic going on at the time. And it really helps them get better awareness and telemetry into their environment. I'm going to talk about a lot of these abstract terms, but at the end of the day, there's still networking is comprised of IP addresses, interfaces, and the like. And we'll go into each one of those layers and how these abstract terms actually translate into the underlying IP infrastructure. We have our service layer. I'll go into that in the next slide. And then our policy layer, which really describes the service level agreements, the route selection, the multi-path routing or path failover decisions that are made on a service basis. So services, what are they? You could think of them as the sinks of your traffic. It's the destination for anything in your network. It could be an IP phone. It could be canonically like your Netflix or your WordPress or YouTube. It could be your print server. It could be anything that is the destination of your traffic. And from that destination is really where you start tying in the policies for how traffic flows and gets steered through your network. Simple in concept, but a really powerful one at that. I mentioned briefly the notion of this conductor. And I'm going to take a sort of a step back from the data model just to describe how the conductor sits, where it's deployed in the network, and its role and function. So the conductor, as I mentioned, is an orchestration monitoring platform used for zero-touch provisioning. All of the configuration resides on the conductor for every single router. So it has a complete view of the entirety of the network. That plays an important role as I build out the rest of the slides, to wherein it actually has complete view of the network, which means it has the understanding of how each one of the routers are interconnected, and then in turn builds out the topology between them using those natural language terms like neighborhoods that I'll get into. The conductor's role, while strictly not necessary, is used in every single one of our customer deployments because of the value that it provides. As an aside, you can actually do all of the work that the conductor does through configuration, configuring them independently on each 128T router. But why would you? And then these are the concepts that I've mentioned earlier in terms of what ties the 128T SVR together.
So the first question that's generally going to come up with something like this is, in the situation where you lose connectivity to the conductor,
right?
What's the state of the network, and how does that move going forward, especially as new sessions are spun?
Yeah, sure. That's an important point. And I think what distinguishes the 128T from other SD-WAN solutions, the conductor, some of our competitors in this space or other SD-WAN solutions have a concept like this. This is a gateway device or a signaling central point. If you look to OpenFlow, that model of a hierarchical control plane, that's not what the conductor is. The conductor is not responsible for forwarding or session setup. If the conductor fails, or if it goes down, or if connectivity is lost intermittently, as all networks have intermittent transient failures, the network will continue to operate. What will happen is any administrative changes that go on through the conductor, whether you're using it to reverse SSH into the 128T router to get individual statistics, if you're looking at getting metrics through the conductor, or if you're applying configuration on the conductor that's then intended to be pushed down to the router, for the time where it's disconnected, those changes won't be applied. But once it reconnects, it'll restore and establish that connection.
Okay.
So ultimately, the data plane doesn't freeze, but your management plane's frozen for the time.
That's exactly right. Yeah, and we felt that was critically important. When we started, we looked at sort of the OpenFlow model, and we realized it just didn't scale. And not only that, it had really what we felt was a fatal flaw in that any failures, the higher you go up in the hierarchy, had larger and larger catastrophic effects on the network. And so we knew that ultimately that each 128T router needed to run independently for as long as possible. And we'll dig into a little bit of that as well. But ultimately, all of the smarts from a routing perspective, all the RIB and the FIB reside entirely on the 128T and are not dependent on the conductor for a control plane and routing decisions.
I have to imagine that you're deploying conductors in clusters and distributed all over, however you do it, for fault tolerance, and that you're really not looking, or rather anticipating, an entire conductor ecosystem failure, but it's probably a branch office or a local failure, so it can't speak to the conductor for some reason, right?
And that's exactly right. Yeah, yep. And that's been sort of the case for most all of our deployments.
In clusters. I mean, I don't put anything out there for a customer as a single VM or a single thing. So.
Speaking of which, my next slide after this one talks about how we deploy for high availability. Our cluster is a combination of two devices. I'll tell you a little bit about the history, but so the node is a concept that's unique to us. It really represents the logical entity that is either a physical piece of hardware in the white box solution case, as you were mentioning, but also as a virtualized endpoint. So minimally, a router is a single node. And the reason why we came up with that concept is because the collection of two nodes represents a shared state. And there's fate that's shared between them within a single 128T router. And the reason why we say it's a single router is because just that, there's a single RIB between them. So all of that session state is shared between each of the nodes. That's important to understand how routing decisions are made at the branch or at the head end as you deploy the 128T router. Another thing that I'm not sure was mentioned earlier is that What's unique to our solution is that it's exactly the same piece of software that runs on every single device, whether that be the branch router, the head end, or even the conductor. It's simply the matter of configuring a different role for the piece of software that changes its behavior. That allows us to really accelerate our development, minimize the amount of defects because we're fixing one code base instead of 3, and allows us to have consistency in behavior and code base on an ongoing basis. So at the end of the day, a router ultimately needs to connect into your network. You need to define what physical interfaces, whether they be Ethernet interfaces, whether they be T1 or LTE. That is what is a device interface. It's what you'd come to expect. It's effectively ETH0, right, when you're provisioning something in Linux. The network interface is that virtual construct that can or optionally have a VLAN. And then with that, we've come up with 2 other constructs. Adjacencies, which are consistent with what you might expect in routing. And then a new term that we've come up with called neighborhoods. I'll go into that a little bit later, but neighborhoods are really describe the topology of your network. Talking a moment about high availability. And this approach to high availability from a clustering perspective is true not just for the router, the 128T, but also for the conductor. The only difference is the conductor doesn't have a forwarding plane. It doesn't run a routing engine instance, and so it doesn't have a RIB or a FIB. But all of the same services that manage configuration reside on the same platform, and you deploy it in a similar fashion. Bit of history, we actually designed the software to be highly distributed. Adhering to the principles of distributed networking and service-oriented architecture, we realized that in order to maximally achieve resiliency, you want to do orders at odd numbers, so 3, 5, 7. We don't deploy that way. We only deploy in nodes of 2, but we can achieve maximal resiliency in much, much larger scale deployments with our software. So each node here sort of represents WAN interfaces as each of our device interfaces, LAN interfaces. And then we have 2 interfaces that are used to interconnect these nodes. We have something called an HA sync interface, which is what is used to communicate all of the session state between each of the nodes. It's used to push configuration between them. And then we have something called the fabric link. And an analog to the way the 128T software was designed is that when we originally created it was that, think of the large-scale chassis core routers where you'd have the line cards and they'd share a common backplane fabric. That's really represents this fabric interface. In Linux, if you, for some reason, felt that you had a faulty network or unreliable switches, you can create teamed interfaces to increase the number of connections between the nodes to ensure greater resiliency between them. We support the notion of link redundancy by way of gratuitous ARP. So if they were connected to a switch, which we would recommend from a deployment, both north and southbound, that through the use of a shared MAC address, that as soon as a single interface failed, sub-second failover could be achieved by redirecting traffic out that other interface.
But these are operating in a hot standby, not a active.
Yeah, so that's an interesting point. So the 128T actually does run in an active mode. Okay. So it's not a hot standby. Okay. You could arguably provision it that way. It's maximally flexible. Mm-hmm. We support a notion of redundancy groups, which is a little bit confusing of a term, but where these 2 interfaces, the WAN interface and this LAN interface, would share fate. Yep. So a failure on one, despite being a failure on the other, will cause all of the traffic to switch to this other node. In that case, this fabric link is not used. In the case of this failure that I've highlighted here, this northbound interface fails. If traffic was ingressing this southbound interface, it would, depending on the service policies, and we'll get into that, it could get redirected out through this node and through this interface. So there would be absolutely no changes and impact to that TCP state. And that's particularly important for services that are relying on TCP, because this way, if you have NAT rules set up, you're not changing WAN interfaces, your source NAT isn't going to be affected. So the traffic really is unaffected by the result of any kind of failure. For node failure, if this entire node were to have gone down, as I mentioned, the state would be shared and synchronized. If you configured the LAN side interface to use a shared interface, subsequently it would be the same thing as the redundancy group. All the traffic would swap over to node B. Answer the question?
Yeah.
So when they're doing active-active, is, say, node A responsible for session 1, node B for session 2, and they split them that way? Or how
It's entirely controlled by the service policies that are associated with the service. So we'll get into that, but we have this notion of vectors that are used to define preference for links. Think of it as administrative cost. And that, depending on the service policy, which also defines your load balancing algorithm. So if you're so for instance, if this was a LTE interface and this was a broadband interface, you may not want to load balance. You may want to say, I'm going to use the LTE as a path of last resort. And so it wouldn't load balance. Maybe if there are two broadband interfaces that were using shared fate, then it would, you can set up a policy. And we also have different load balancing strategies that define proportional algorithm, which is something that we've come up with, which looks at the amount of traffic on a given link and the link quality and allocates bandwidth and the session count accordingly. We also have policies of hunt, so it'll maximally fill up one link and then switch over. And then we have just the typical round robin, which will go back and forth. So
and there's application policy routing. So I want to send this type of traffic out LTE because I don't care as much, that kind of thing, right?
That's exactly right.
Which is important.
Yep.
Yeah. Okay.
I already spoke about that. We've referred to that as the dog leg interface because of sort of this, it follows this path, but it's really the fabric interface. All right. Tenants. Tenants are the complement to services. They're really important to understand, and we use this term, and it's probably the cause of a lot of confusion. Tenants are while the services are the sinks of the traffic, tenants are the sources. They're really important to understand as a complement in the sense that they define the access policies to the service. In short, they are the group of users or devices, or a group of users that control access into your network. They can't ultimately, a tenant can be defined by way of one of three properties. One, I don't know if we've gotten into it yet, but we have this notion of metadata. Metadata is the sort of the session state that we pass along in the first packet during session setup, communicated by and across 128T routers. If that originating packet contains a tag, a TLV tag of a tenancy, so this way we know where it came from. Case of an example, you have a branch router, it has a network. You may construct a tenant, say engineering. Engineering may not exist as a network interface or a construct in the data center, where's your head-end router. And so you need to traverse that information of the origin of that packet throughout your network. And as Ritesh was mentioning, the session state is preserved all throughout your network across n number of hops. So this way you have complete visibility all throughout your network. And that's really important, both not necessarily from telemetry perspective, but really from an operations perspective, getting full optics and understanding how to plan and provision your network. Tenancy can also be defined by way of network interface. So if I had a network interface which is on my northbound side in my data center, all traffic receiving from that switched fabric, I could ascribe to a given tenant. Tenant can also be described by way of IP addresses. So on the neighborhood, and I'll get into that, you can define exactly the CIDR block that's associated to that tenant. So it really affords you the ability to have maximum configuration flexibility in determining who has access into my network. Think of it another way. In terms of mobility, And the reason, and tenants are defined in a hierarchical scope by way of names. Really, it's nothing more in our data model than just ascribing a label. I use the notion engineering, and it follows a hierarchical fashion where it's child and it's dotted notation. Think of it like a DNS name where it's engineering.128 technology. Engineering is the child tenant, 128 technology is the parent. In terms of access policy, if you were to associate a service foo with tenant red as the parent, we'll just call it parent tenant, it's a little easier to follow, then any child tenants, in this case engineering, would have access to that service. But the converse is not true. It's kind of like what the kids would prefer, right? The parents don't have access to the kids' room, but the kids have access to the parents' room. And tenants really, the reason why we came up with this abstract concept is because we knew that in a world of high mobility, when you take your laptops that you have in front of you and you take them to a different office location, that we really want that identity to follow the user or that device, not an IP address that is constantly changing from network to network. The notion of user identity is abstracted in our term by the way of a tenant. Neighborhoods.
So,
yeah,
and tenant is important. Let's spend a couple of minutes.
Sure.
So, let's talk about tenant in a case of cloud host. I'm in AWS and I have a virtual IP address, and that virtual IP address can be assigned to a VPC, etc. So, you're saying I can associate from a client child, I can say, you know what, this tenant is this VIP. And then this virtual IP can have another, that can be a parent, then a child of that can be a bunch of services behind that. So a tenant would be, let's say, I'm going to say something crazy like VoIP running on behind this set of IP addresses, or this IP address is a tenant, and that tenant can be physically anywhere within my VPC. So I've abstracted away the concept of the tenant away from the physical host it may be on.
That's exactly right. And tenants are one of those constructs that are global in nature. And that's very important, because in the example that you just described about the cloud infrastructure, you could define the same tenant from a policy perspective to be in your cloud infrastructure, your data center, or in your corporate network environment, abstracting away the IP addresses, right? The approach that we've taken is that we really feel like IP addresses don't really describe intent behind the networking. And I don't mean that in the Cisco intent-based networking sense, but really that IP addresses are constantly changing. It doesn't really matter if your IP address is v4 or v6. It should define who you are, or that service is, or whatever it is that is originating the traffic.
Now, what would be really cool would be if I had a VM tenant, a tenant that was described around a set of labels of like VMware labels that says, you know what, this is my web hosting, or my, more specifically, let's say engineering. These are my engineering desktops. And my engineering desktops have these VM labels, and those VM labels can exist either on-prem or in my VMC on AWS cloud and protected by this data model. That's
exactly how it works. That's exactly how it works. We have actually here, obviously we use our own product for our own needs, and we have resources both in the cloud. We have a co-location facility, and we have some equipment here, and that's exactly how it's described. We have a hierarchical model that we define those engineering resources, and despite where they reside and the addresses that they have, the policies follow suit. Neighborhoods are another really important construct that really is fundamental to how the routing decisions are made within the 128T platform. Some people say that the 128T within an authority is like a single distributed router. And it's not entirely wrong concept to think of it that way. So a neighborhood really can be thought of in some fashion as in a directed graph network that your routers are your nodes, obviously, and then your neighborhoods define the edges of your network. And what it's used for, by the way of the conductor today, is to automatically go through the process of provisioning peering relationships between 128T routers, as well as the corresponding adjacencies between them as well. They have other properties as well, which is the notion of vectors, which I'll get into next, which defines path preference. But just as important, is the property of those neighborhoods that govern their behavior. So like tenants, neighborhoods are nothing more from a data model construct as an identifier, as a label. You call it whatever you want. Some examples are just following broadband, so that you could use that as sort of a logical representation, saying, okay, I know that I want to apply preference by way of broadband. We came up with these notions of mesh, hub, and spoke, fairly common in networking. And so depending on how you provision your neighborhood, and the neighborhood is configured on a network interface. So each network interface can be in one or more neighborhood. Perhaps I could describe a little bit on the whiteboard with an example. Each of these being 128T routers, each of them with these neighborhoods between them, interfaces rather. And we'll just call these N1, N2, N3, and 4. If I configure this as a spoke, and a spoke, and this is a hub, and this is a hub, if these are in the same neighborhood, I'll change this to N1, sorry, and N1, they're both in the same neighborhood, spokes connect to hubs. So what we've done automatically by way of just describing these interfaces to be in the same neighborhood, the conductor now knows that these two routers effectively are in the same layer 3 network. They're mutually reachable by way of layer 3. If these two are in different neighborhoods, there's no work to be done. If this one was also in neighborhood 1, these two can now communicate. And these two being spokes, they don't communicate to each other. If I change this to a mesh, these two now would communicate, would create a peering relationship between the two. So it's the combination of between hubs, spokes, and meshes that you really define the entirety of your topology. So you might ask, well, why do I need this notion of a neighborhood? What does that really afford me beyond just defining explicit adjacencies between them? Well, another important point is I could actually define multiple network interfaces to be in the same neighborhood. And this is really where one of those basic use cases of SD-WAN come into play, because now I could have multiple paths between 128T routers and use that for session resiliency, packet duplication, multi-path routing, path failover, and then I apply the policies to those neighborhoods to make those decisions. Building on that last example with the multiple network interfaces, peers are really nothing more than two interconnected 128T routers. Minimally, they have one interface that's shared between the 128T routers, but really you want to create a peer for the purpose of having multiple paths, whether that be a single interface connecting to two distinct interfaces on an adjacent 128T, the converse, or one-to-one on each side. The reason you would leverage this is exactly like I was saying before, for path SLA, for path failover, for multipath routing. That's really where peers come into play. Adjacencies are the individual pathways that are established within a peering relationship between 128T routers. Ultimately, at the end of the day, once the conductor understands the entire topology and directed graph, making sure that it's all loop-free, for each one of the adjacencies between 128T routers, automatically we set up BFD negotiation between those two pathways. And ultimately that BFD is used not just for link failure up-down, but also is the mechanism in which we determine jitter, latency, and loss for each one of the paths. In a not too distant software release in the future, we're augmenting our path quality metrics to leverage what we call inline flow performance monitoring. Slightly different take on sort of the coloring of packets, wherein we can then determine the quality of service for each of the services by path, by traffic class, by interface. And that's particularly important because, as you might imagine, you say, okay, BFD is great and all, but it may suffer the fate of being marked differently than my service traffic. So how do I really get a good sense of what the quality of service is for that particular service? Going over the same link, right? I mean, we all know that routers once traffic engineering kicks in, is once you're at your bandwidth capacity. So decisions are going to be made. So do you favor BFD? And if BFD has preference, then maybe that's not representative of what that particular service is, especially if it's going over a best effort path from a traffic engineering perspective. Vectors. In that example that I made with the peering path between two links, this oversimplistic example between two 120T routers, if I want to define a path preference between the two, I use the term a vector. And a vector is a label that you associate with a neighborhood. Now, if these are in the same neighborhood, then you couldn't describe two different vectors. But so in this case, it would be two different neighborhoods connecting two different 128T routers. And then the service policy, and this is an important point, is the path selection decisions for SLA are made on a service-by-service basis, not on describing the topology. And so for each service, I could describe a different cost. And you might, a classic example of that is many of the SD-WAN deployments that we're involved in, they still use T1 links. They want to prefer T1 for voice. They want to use their broadband effectively for internet offload or any of the other services they might have. And so you can define a different cost per service. In this case, we'll make MPLS, or like the T1 interface, higher cost for everything else, our service D, and the converse could be true for the other alternate path. Just a bit about how we determine path selection. Think of it sort of like a bandpass filter for those electrical engineers in the room. What we do is we determine first path availability by way of whether the link is up or down, and then if the service level agreement is being met by way of the definition of the service policy. And you can define that either by jitter, latency, loss, or MOS. Not all four simultaneously, obviously. If it meets the SLA, then we go through, depending on the load balancing strategy, then we go through the process of using the vectors to determine the best optimal path as a follow-on. And then, as traffic is being steered from one to the other, and if path failures occur, if the service policy is dictated to do so, it may revert back. We have something called revertible failover. So you fail to your backup path, and then once the primary or preferred path is restored, we can restore the sessions back to that path.
May I ask a question?
Sure.
Related, but not directly to what you were just saying while we're waiting? So I've noticed some terms that were reminiscent of some research I've been doing in intent-based networking. You've mentioned data modeling, graph theory, things like that, and a lot of network abstraction, which we hear with other SD-WAN vendors for sure. But because you have those components now in place, are you able to, or maybe thinking about doing some sort of network modeling on the WAN for like staging, pre-staging before committing to a config, that sort of thing? Doing kind of testing of how could these pathways work with this new traffic before deploying into prod?
Yeah, that's a really interesting point.
I know it's a different thing, a different component that would have to be developed on its own, but I asked.
Sure. So I'm familiar with, and I think there's a company that does effectively that. What they do is they model the traffic, and then you describe the configuration of the topology, and then it takes that traffic and it tries to apply it to that model and sees if it
Right.
would be a good fit.
Well,
You know,
I ask because if you have the state of the network,
Sure.
because you have everything from the devices themselves, and you have all of the configuration there, so you know what the current production and all the
Yeah.
state of the current
Correct.
traffic movement. It seems like it could be a
Yeah, absolutely. It would not be a far reach to be able to implement that sort of functionality in our product, but we don't have that today.
So, higher level question again, from a lot of cool nerd knobs, which is great, but we know, so the industry is kind of moving in two different ways. Network geeks who love nerd knobs, and then kind of enterprise geeks who say, you know what, network guys, you know, I know you've been doing this for 20 years, but I'm smarter than you. So I kind of have a bias towards no nerd knobs. So the whole concept of I should always select the T1 link for voice has been this traditional view, and this helped me set that up. What if I'm just, you know what, I don't want to do any of that. I just want the best selection, least jitter for this application to go over the best path. And that path could very well be an indirect path. I don't want my networking people who I want them working on other smarter things. I don't want them figuring out paths.
Sure.
I want them figuring out something else. Can I come to 128 Technologies and say, you know what, just figure out, kind of an extension of Phil's question, figure out, here's my applications, here's my policies, here's my preferences for this stuff. There may be a path in my network as a network engineer that the data is, I can't analyze all the data. The tool is telling me is a much better path than I would have came up with natively.
Yes, great question. You know, this company was founded by a bunch of nerds, so it's unsurprising that there's a bunch of nerd knobs in here. And you're also right that our customers kind of fall into two camps. Those who really want the full control of the network and really prescriptively define every single pathway and engineer every single session across a specific path. And then you have the other camp who, as you all know, that the trend is moving away from companies doing their own IT, and it's becoming outsourced through a managed service. They don't have, it's not their core competency. It's not providing any value to them as a business. They're looking for that easy button. One thing that's may not be obvious by way of describing the data model is that what we also believe in that trend. And we feel that every single configuration of your network should not have to go through IT or networking admin. So the notion of that tenancy that I mentioned earlier is really in the spirit of that as well, which is to say that the business unit should be able to have control and governance over their services, not having to go to, hey, Mr. IT, can I please, have this, network interface set up so I can have my engineering continuous integration function set up, and I don't care about that. I trust that someone else has already built out the network. I know what I need from a service and application perspective. I can entrust through the construction of the topology by way of maximally selecting paths. And the way that you would do that, to now get down to the heart of your question, we have two interfaces here in our HQ through two different providers. Right now, almost all traffic is steered across both. And it utilizes the best path for that service based on the SLA. So it already achieves exactly what you're describing. And the beauty of it is through tenancy in the way that it's traditionally thought of, that business unit owner, in the case for me, like if I were the engineering lead, I could set up that service in my network without having to really worry about the underlay.
So as we get into models, you talk to kind of developer. We talked about this a little bit last night at dinner, which is I don't really care about the underlay. I'm creating an application. From a notional perspective, I know my IoT and data user data traffic shouldn't be on the same network. I don't know how to, other than, I'm writing a Kubernetes-based application, other than I know to set up 2 different network labels and network abstractions and say, this is the security policy I want. Have you guys made that connection from literally from Kubernetes where I can say, hey, here's what I want from a security policy, IoT, one network path or one separate network, and then user data traffic for this overall application, different segmented set of security boundaries, make it happen.
Yeah, so we don't have that functionality directly in the product, but we have had customers or partners do exactly that. So I didn't talk about it, but our data model is written in Yang. And if you know Yang, it's sort of the complement to netconf. And our configuration can be managed through northbound, REST interfaces or netconf directly. And it's entirely extensible and programmable. And so those customers and or partners have developed rules so that you can tie directly from Kubernetes, bringing up a resource, defining a network, and then correspondingly setting up the policies in the 128T automatically. So there's sort of that sort of configuration shim layer, if you will, that maps those 2 different network infrastructures together.
Okay. I have a similar question, almost in the same vein, but I think a little bit different, and that is, this room full of people loves all the nerd knobs and understanding how
Sure.
it works, right? But there's like a minimally viable configuration for someone to get started with something like this, and I'm curious, are you having to touch all of this, or is there for someone who doesn't want to engineer to that degree, what's the challenge of getting it implemented? Because everyone says simple. I hate that word, by the way. But
Yep.
everyone says, it's simple. We're going to put
Sure.
it in. There's always some level of complexity, but the idea is how much engineering do you have to do versus how much engineering do you have available to you?
Yeah, it's always simple for those people who have intimate knowledge
Once
in
you
the product.
spend 10,000 hours doing this, then
Right.
it's all very, very easy.
Right.
Yes.
And if you take someone from a different walk of life and you explain traditional networking to them, it's not simple.
No.
So it's a fair point to say that people want simple, but they don't really understand what they're asking for. I would say that if you go through our basics training class, you are armed with the knowledge in order to set up the basics of a network. Now it depends, to really build out the answer to your question, what is your network looking like?
There are
right?
requirements. I guess what I'm trying to get at is, there are solutions out there that bill as, we're going to hide everything from you, right? You're going to go in and fill these 10 form fields out, and you're going to have a network.
Sure.
And it's very prescribed. What you're explaining is very, very flexible. And is there some middle ground, right? Because usually the more flexible solutions have a lot more power of what you can do, but they tend to get a lot more complicated to set up.
Sure. So we don't have that easy button.
Okay.
But I would say that you can do a lot in terms of defining your network and topology with very little configuration. It won't necessarily take those engineered pathways for a particular service, but you can effectively build out your entire network from a neighborhood perspective with very few configuration elements.
Okay.
But there's no easy button to get started. Discover my network, figure out what's here, and then set it up.
It's on the
I think I'm
roadmap,
running.
though, right?
It is actually on the roadmap.
Is it?
Yeah.
Just press the button and build
Yeah.
a network?
No, it is. This is my last slide. Looks like I'm getting close on time. So service routes. I had mentioned this a couple slides ago. And, in some ways, service routes can be thought of the glue that ties ultimately the underlay network back to the services model. But really, they define the path that is going to be taken for a given service. So whether that be a peer 128T, I'm sure, and I hope you guys know at this point that the 128T is not a solution that lives in isolation. We interoperate with traditional networking, OSPF and BGP. Our next hops can be non-128T devices or services directly. And that's exactly what the service route is used to describe. For a given service, which is defined minimally as an IP address or IP prefix and a transport, You also define a service route, which is one of those data model constructs that are local in nature, meaning that these service routes are specific to the router at a particular location, whether that be the branch or the head end. Given by the policies that are associated with that neighbor, we can say that, okay, for this particular hop, for this service, foo, I want to make sure that I do path resiliency, path duplication, service duplication. And for this last hop, if you will, egressing the 128T network, I could elect to use a routing policy. So what I've learned through BGP, and it will tell me ultimately which interface to use to egress, whether that be a service instance directly, a /32, and I can do source natting on here to ensure that the traffic is returned through the directed pathway that is set up bidirectionally for each session. Or any number of other means of directing traffic. So ultimately, that's how we steer traffic through the policies of the 128T.
So this, and then a couple things you mentioned earlier reminded me of like OSPF areas and
Sure.
stuff like that. So not exactly in that vein, but thinking hypothetical, let's say I have a few hundred branch locations, or maybe more, 1,000 branch locations, but in divergent regions geographically. So they're not just in the Northeast, but maybe across the entire country. So different ISPs and then different SLAs all over the place. Do you have a concept of maybe like regional POPs, so to speak, a regional hub, 128T routers where I can aggregate things and then back all that to some of the Chicago for the? Does that make sense?
It makes perfect sense. We are not a like networking as a service solution company, so.
Right, but if I were deploying 128 for my 1,000 bank branches across the country or healthcare offices, things like that, all my small branches,
I think maybe the STEP presentation will give a little more insight into
a little bit more color to that.
some of the
Yeah,
aggregation.
I think that's definitely fair. STEP, sort of a sneak preview and teaser to it, is our routing protocol that's used to, instead of statically provision your network, it dynamically understands the network, all of its properties across different authorities or administrative domains, and it figures out the optimal paths like you've described.
So there's enough intelligence that presupposes that's not necessary to
Potentially.
Like everything that Mike's talking about here, without STEP works great as long as you're going one 128T to another like directly and not through another 128T. If you want to aggregate things at a 128T, that's where STEP comes in and helps solve some of these challenges automatically with,
Yeah, so absent STEP, we can accomplish what you've described, but it would have to be explicitly defined. I'd set up that hub regionally and then redirect traffic and sort of backhaul it to a data center or to another centralized hub if necessary.
May I ask what sort of scale you've seen as your upper limit thus far? Maybe not upper limit as potential, but what you've done as far as deployment?
Yeah, sure. So the scale, like security, is sort of a suitcase term. Like it depends on what characteristics of scale you're referring to.
Right.
So there are a number. As I mentioned earlier, our is the same software that runs on the branch router, the head end, and the conductor. And what's really powerful about that is, from a hardware footprint, from a white box perspective, we run on a platform as small as 2 cores. And obviously processors matter, to as high as multi-socket 44-core systems. We can forward traffic, obviously on the slowest end as low as possible, but over 100 gigabits of throughput. So from a forwarding perspective, the scale follows naturally with the hardware footprint that you give it. From a peering path relationship, so those adjacencies that I mentioned, we have deployments upwards of 4,000 peering paths as a hub and spoke model for an SD-WAN. Yeah. From the conductor, we have deployments that are approaching 1,000 routers from a configuration perspective.
So you have no qualms with me going in and speaking to an SMB sort of with 12 locations in an area, or to a large enterprise that's global with 1,000 locations.
That's exactly right.
In either case, we can make both a business case and a technical use.
That's exactly right. I mean, we have customers who are in the many thousands of deployed sites.
Okay.
I think it's actually one of the interesting things as I'm thinking about like the whole tunnelist thing. Because I think one of the big limitations inside of SD-WAN is not you mentioned a hub site. Yep. And the reason why we kind of build these topologies is because the fact that we don't want to put a full mesh out, because that means I got to put a big router at every site because I've got to manage, tens, hundreds, thousands of tunnels at every branch. where because this is session-based and there's not tunnels, there's not whatever, you can do the full mesh, right? You're not building that tunnel for every single site. And so it's only based off the sessions that are going through the router, and so you just have to scale it based off the number of flows.
That's exactly right.
Right.